Okay, now we're working on 10.14 in the AP Calculus BC curriculum. We're going to talk about Taylor series and Maclaurin series and take a look at what we can do with those. We're going to define the Taylor series, and then we're going to use that Taylor series definition to show you that the alternating harmonic series we talked about the other day sums to ln2. We're going to do that by creating the Taylor series of f of x equals ln x and expand that about x equals 1. So first, once you see that a Taylor series is just the infinite series of terms in a Taylor polynomial. Some functions have an infinite number of derivatives, and those functions we can create a Taylor series for, actually. Even a polynomial, we can create a Taylor series for, because after a third degree polynomial has 3 derivatives, and then the fourth derivative is 0, and the fifth derivative is 0, and an infinite on it. So it's still a Taylor series, but it's just a whole bunch of zeros after a certain point. But in general, we're looking at functions that have an infinite number of derivatives that aren't necessarily 0. And so let's look at a Taylor series, what the definition is. The Taylor series is sum for a Taylor series for a function. Let's just write this. A Taylor series for a function f of x centered at, or sometimes said expanded about, x equals a, is the sum, n equals 0 to infinity now, of the derivative of f, nth derivative of f, evaluated at a, times x minus a, to the nth power, all over n factorial. That's the Taylor series of a function. And so, if we look at that, the Taylor polynomial is the nth partial sum for the nth degree Taylor polynomial is the nth partial sum of a Taylor series. The nth degree Taylor polynomial for a function is the nth partial sum of the Taylor series. So let's do an easy one here. Let's just go ahead and do the Taylor series for, let's let f of x equal x squared plus 2x. Now this is a second degree polynomial. There's no point in doing a Taylor series for a second degree polynomial, but I'm going to show you how this works. Okay, so if we want to expand this about, find the Taylor series, centered at or expanded about x equals 1. So this is going to be the sum. We're going to need to find f of 1. We're going to need to find f prime of 1. We're going to find f prime of 2. After f prime of 2, the third derivative of a second degree polynomial is going to be 0, but we'll show you f prime of 3 and f prime of 4. So f of 1 is easy to find, that's 3. Now f prime is going to be 2x plus 2. F prime of 1, oops, it's supposed to be 1. This is going to be f double prime, f triple prime of 1. Forgot what I was doing there for a second. And this is all derivatives evaluated at 1. That's what we need to find for this. So f prime of 1 is going to be 4. F double prime of 1, we need to find f double prime of x, that's just going to be 2. And so f double prime of 1 is going to be 2. And then f triple prime of x is going to be 0. And if we take the derivative of 0, we get 0. And you can see that from now on forevermore, these terms are all going to equal 0. So that when we plug them in here in the Taylor series, all those terms are going to be 0. So the Taylor series expansion of f of x, this function, about 1 is going to be, the Taylor series expansion is going to be n equals 0 to infinity. It's going to be, of f of x, the nth degree of 1, the nth derivative evaluated at 1 of x minus 1, it's not squared, it's to the nth power, over n factorial, is going to equal, remember, the 0 degree, or the 0th derivative is going to be just f of 1. This is going to be f of 1 plus f prime of 1. Since we're expanding about 1, we're going to do times x minus 1. That would be over 1 factorial. This would be over 0 factorial, but those are both 1, so we don't need them. And then we're going to have f prime, double prime of 1 times x minus 2, or sorry, x minus 1 squared over 2 factorial. And then f triple prime of 1, we already said it's going to be 0. So when we multiply that, f triple prime times x minus 1 squared, we're going to get 0, and then f the 4th derivative, and so on and so forth. All the rest of the terms are going to be 0. So what this says is that this Taylor series expansion becomes f of 1, which is 3, plus this is f prime of 1, which is 4, times x minus 1, plus f double prime of 1, which is 2 times x minus 1 squared, all over 2 factorial, and then a bunch of zeros after that. But that is the Taylor series expansion. So really and truly what this should all equal when we get finished, it should equal the original function. A Taylor series expansion of a polynomial should be the polynomial itself. Let's see what happens here. Because this is going to be 3 plus 4x minus 3. And this is going to be 2 factorial, 2 over 2 factorial. Since 2 factorial is 2, these are just going to cancel. And this is going to be an x minus 1 squared, which is x squared minus 2x plus 1. And so this should be minus 4. Just looking at the 3 when I wrote it, I guess. So we end up with 3 minus 4 plus 1 is 0. We end up with x squared, and then plus 4x minus 2x, x squared plus 2x, which is the original function. So the Taylor series expansion, in a lot of cases, can end up being the function itself. This is even true when we have infinite numbers of infinite number of terms. So an infinite number of derivatives for the function, we end up with an infinite series. That time we ended up with a finite series. So let's take a look at this example we were talking about. And what we're going to do is we're going to expand, find the Taylor series. For f of x equals ln x, expanded about x equals 1. So if we're going to do this, we need to establish what this is. Let's take a look at this. Let's find f of 1. F of 1, ln 1 is just 0. Then we're going to need to find f prime of 1. We're going to need to find f prime of 2, f double prime of 1, f triple prime of 1, f fourth of 1, and let's see if we can establish a pattern by the time we get to here. So we know that f prime of x is 1 over x, so that f prime of 1 is just 1. This is the same as x to the negative 1, so we know that f double prime of x is negative x to the negative 2, which is just going to be negative 1 if we evaluate it at 1. Oh, we got to put that. Yeah, negative 2, negative 1. Let's do f triple prime of x. That's going to equal positive 2 times x to the negative 3. That's 2 over x cubed. Evaluated at 1 is just 2. Let's go ahead and do f the fourth degree, our fourth derivative. That's going to be negative 6x to the negative 4. Negative 6 over x to the fourth power. When we evaluate at 1, that's just going to be negative 6. Let's go ahead and do the fifth derivative also. Evaluated at 1. It's the fifth derivative. It's going to be 24 times x to the negative 5, or 24 over x to the fifth, which again is just 24. So let's take a look at what's happening here. And we see that this Taylor series expansion for ln x, now this is the Taylor series expansion. This is saying that ln x is equal to, and we said f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 times x minus 1 squared over 2 factorial plus f triple prime of 1 times x minus 1 cubed over 3 factorial plus the fourth derivative times x minus 1 to the fourth over 4 factorial. And I'm going to put this up here, plus the fifth derivative times x minus 1 to the fifth of 5 over 5 factorial and plus, and it just keeps on going like this. So let's see where this is going with this pattern. We've got 0 for f of 1. F prime of 1 was 1. So this is going to be plus 1 times x minus 1. And then we had minus, and this was going to be x minus 1 squared, because after all these derivatives were, oh, no, we got to put those in. Minus 1 goes here, times x minus 1 squared over 2 factorial plus f double prime, or f triple prime, sorry. F triple prime is going to be 2 times x minus 1 cubed over 3 factorial. And then we have the fourth derivative was negative 6. This is going to be negative 6. Let me go ahead and get the eraser again there. So this is going to be negative 6 times x minus 1 to the fourth over 4 factorial, and then plus 24 times x minus 1 to the fifth over 5 factorial. And we said this keeps going on and on and on. So the reason I want you to see this, I want you to look and see what's happening here. Let's evaluate this and see the zero's gone. This becomes x minus 1 minus, now 2 factorial is just 2. So it becomes x minus 1 squared over 2 plus, and this is going to be 3 times 2 times 1, or 3 times 2. The 2 on top and the 2 on bottom cancel, and this becomes x minus 1 cubed over 3. And this becomes 4 times 3 times 2 times 1. This is 4 factorial. That's 24. 24 is 4 times 6. So 6's cancel, leave me with 4 in the denominator. This becomes x minus 1 to the fourth over 4. Here, 5 factorial is 120 because 5 times 4 times 3 times 2 times 1. 24 is 4 factorial. So this becomes just 5 times 4 factorial, 4 factorial on top. This cancels and becomes plus x minus 1 to the fifth over 5. So now you might be able to see that the next term in this series is going to be x minus 1 to the 6th over 6. And the next term would be x minus 1 to the 7th over 7 plus, just keeps going like this. This is the alternating harmonic series if we plug in 2 for x. If we plug in 2 for x, what we see is ln2 plugging in for x is equal to 1. We plug it in here, minus 1/2. Plug it in here, we get 1 on the numerator. We get plus 1/3, minus 1/4, plus 1/5, minus 1/6, plus 1/7. And this pattern continues forever indefinitely. And this is why we said, when we defined the alternating harmonic series the other day, that L converges to ln2. But this is the proof of that, because when we do the Taylor series expansion about x equals 1 for ln x, and then we evaluate ln x using that expansion at 2, we get the alternating harmonic series. So the alternating harmonic series, the sum from n equals 1 to infinity of 1 over n factorial times however we want to make it alternate. Let's say 2n minus 1. No, n plus 1 is what I need to do. That's going to be the alternating harmonic series. That sums to ln2. And we can show that using this Taylor series expansion. Let's go ahead and do a little bit more here. No, we'll go ahead and introduce on the next video the Maclaurin series. Okay, all right, we'll stop sharing and we'll get on the next video of the Maclaurin series.